So I'm your module tutor, Lois Gray, for the Electrical Power Unit or module in the degree. So today we're going to do a laboratory on a three-phase half-wave controlled rectifier circuit. We have here the feedback rig, and we have the three-phase supply set up down here, and that's around about 110 volts RMS. We have our three-phase half-wave rectifier configuration here. And we're going to look at controlled rectification. So you'll see that we're using thyristors in place of diodes. And hopefully you'll remember that a thyristor is very similar to a diode, but it can be put into conduction by applying a gate pulse at the gate point here. Because we're using an AC circuit, these particular thyristors will naturally commutate, so they will switch off by themselves when the voltage drops below zero, as it does with an AC signal, and the current drops below the specified holding current of the device. So we'll see that when we do the lab anyway. We have the rectifier circuit driving a resistive load up here, and we have switched the inductive load out of the circuit with a short circuit here. So at the moment we're just going to look at a resistive load, and we will move on to looking at inductive loads in the next laboratory. Now, in addition to that, we have some measuring equipment connected. Here we have a voltmeter which is going to measure the DC voltage. We have another RMS voltmeter here, and we also have an RMS ammeter that will measure our current coming out of the circuit, or current flow through to the resistive load. And we have a mean ammeter which will measure the mean current flowing to the resistive load. So the intention of the circuit is that we're able to control the DC voltage and current by adjusting the firing angle with this knob, so that our thyristors are held off for a portion of the rectified waveform and switched on at various angles. We can see the waveforms on the scope here. The yellow waveform number 1 is voltage, where one division is 50 volts, and the blue waveform is current, where one division is 1 amp. So you will hopefully see the effect of varying the firing angle on both the waveforms, the voltage output, and the current here around here. Okay, so we'll just get started. So we'll start with a firing angle of 0 degrees. So this will give us our maximum DC voltage output, and is indeed what we would get if we had a half-wave rectifier using diodes as opposed to thyristors. So essentially we are switching on the thyristors at the very earliest possible time when they would naturally come on anyway, if they were diodes, and the circuit effectively looks like a bridge rectifier with, a half-wave rectifier with diodes. Okay, so if we turn this right up to the firing angle of 0 degrees, we can take some readings. So we can see here that our voltage at this point, our DC voltage at this point, is 123 volts. Okay, our RMS voltage looks very similar to that, around about 130 volts maybe. Our RMS current is around about 0.5 amps, and our mean current is 0.11 amps. Now, observing the waveforms, this is quite important. We are firing the thyristors on at this point here, which would equate to 0 degrees, which, if you have a look at your theory for three-phase half-wave rectification, you'll know that if we use a reference waveform that's our typical sine wave, where the instantaneous voltage equals the peak voltage times the sine of the angle, this point is actually at 30 degrees. So it equates to a firing angle of 0, but it's 30 degrees from the reference point of a normal sine wave, or of our reference sine wave input. Right, you'll need to probably have a look at the templates I've given you for working out what I mean by all that. And you can also have a read of the notes in the experiment lab manual. Okay, so we'll now turn the firing angle up in 10-degree intervals. So, starting here, so I said that was at 0 degrees, so our next angle will be 10 degrees firing angle, an actual angle of 30 plus 10 degrees. From our reference waveform, and that will give us a waveform that looks, I turned it a bit too far there, a waveform here that looks like that. Okay, so hopefully you can now see on the oscilloscope display that the current, of course, is in phase with the voltage because we have a resistive load. But instead of turning our thyristors on at the sort of crossover point of the phases, we do actually have a delay. So this would be the crossover point of the phases here, and there's a 10 degrees delay between that point and the point at which the thyristors switch on. And then once they've switched on, they then follow that particular phase of the three-phase input supply. We're talking about phase voltages here, by the way, so as I said, we've got about 50, 100, nearly 150 volts peak, or around about 150 volts peak. So if you work that out, you should know that peak voltage is √2 times the RMS voltage, and I said we had an RMS phase voltage of about 110 volts, so that seems approximately correct. Taking some measurements at this 10 degree firing angle, we have around about 121 volts DC, about the same on the RMS meter here, again about 0.5 amps on the ammeter, RMS ammeter, and 0.15 amps on the mean ammeter. Right, you'll notice that the waveform is entirely positive, there's no negative cycles of this waveform. That's because of the resistive load. So now if we turn up to 20 degrees, that's round about that point there, I think. Yeah. So again, all that's happening is we're delaying the firing angle of the rectifier coming on, or the thyristors in the particular phase of this rectifier coming on. So if our crossover point was about here, we now have a bigger delay angle, and the thyristors aren't actually firing on until this point here. And then again, they then follow the three-phase input, the particular phase that those rectifiers are on for. Right, we have, at this stage, we have 114 volts DC, approximately the same RMS, still around about 0.4, 0.5 amps RMS, and 0.2 amps mean. So I'm going to carry on, that was 20 degrees I think. Now go up to 30 degree firing angle. So a 30 degree firing angle is probably round about there. Okay, so again, remember we're measuring from the crossover point our firing angle, not from the zero point of our reference sine wave. Okay, so at this point we have 105 volts DC, approximately the same on the VRMS meter, again 0.4 amps on the amps RMS meter and 0.24 amps mean, and you can still see both the current and voltage waveforms on the scope there. Remember the yellow one is voltage 50 volts per division, the blue one is current at 1 amp per division. Right, turning down or up our firing angle now to 40 degrees. Okay, that's about there. Taking the readings again, you can hopefully see what's happening now. There is actually a portion of the waveform where there is no volts at all, because we've reached the natural commutation point of the thyristors that are causing this portion of the waveform to be conducted to the load. Anyway, we have a DC voltage of 92 volts, or 93 volts. We have an RMS voltage of about 110, an RMS current of about 0.4 amps, and a mean current of 0.28 amps. Okay, so we'll carry on and go up to 50 degrees. Yeah, we haven't done 50 yet. Okay, there's about 50 degrees there. So again, the portion of the conduction period which sits at 0 volts is now a lot longer. So the load is actually receiving no volts for a longer period of time. So our DC voltage is dropping to 76 volts. Our RMS voltage is around about 105 volts perhaps. Our RMS current is about 0.3 amps. and our mean current's 0.31 amps. When you are doing the calculations for working out the DC voltage for the circuit, bear in mind that the thyristors do indeed have quite a large voltage drop when they're conducting. So the answers you get will not work out exactly as per 110 volts RMS phase input. Right, we'll carry on now to 60 degrees. At 60 degrees I would expect the waveform to only turn on as it reaches its peak, and we'll have quite a long period of non-conduction or thyristors being completely off. So that's going to be, I would say maybe about there. Okay, so the waveform, at this period there's no thyristors conducting, and then at this point the two thyristors in the particular phase of one of the three phases come on here. They follow that phase, or they conduct for the rest of that phase, and the output voltage follows the input voltage minus the thyristor diode drop or thyristor forward drop, and then they sit again with no voltage output because the thyristors have naturally commutated at this point and are remaining off until the next set of phase thyristors is fired on. Okay, at this point we have 58 volts DC, approximately 90 volts RMS, 0.2 amps RMS and 0.3 amps mean. Right, carrying on now to 70 degrees. So progressively we're switching more and more of the input voltage off, or we're not conducting more and more of the input voltage, and our DC is dropping further and further. So down at 70 degrees we're not going to have a very high DC voltage at all. So we'll go down to there. That's about 70 degrees. We only have 38 volts here, about 30 odd volts on our RMS meter, around about 0.2 amps or maybe 0.1 amps RMS and 0.24 amps mean. And then coming on to 80 degrees, we almost have completely switched the thyristors off for the full cycle by this point, so the output voltage is very low. So our output voltage now is only 16 volts. Our RMS output voltage is about the same. Our output amps RMS is nearly zero, and our output current mean is 0.13 amps. And again, you can see the waveforms here. And then finally, going down to a firing angle of 90 degrees, we will actually not be firing the thyristors on at all. So there is no point now at which the firing pulse occurs when there is a positive voltage across the anode to cathode of the thyristors. So we have no voltage and no current. So hopefully you can see how we can control the DC or mean voltage going to our load by adjusting our firing angle for this three-phase half-wave rectified circuit. Okay, the next experiment will be looking at the inductive load, so I'll just switch the video off just now, set that up, and then I'll go on to doing that. Thanks for listening. Bye.